As you may have discovered when working with the Shockley diode equation, solving circuits with p-n junctions using this equation can be difficult. When using a BJT as an amplifier, the designer needs to have a method of analyzing BJT circuits more easily. We use a method called perturbation theory. This was explained for a diode in earlier videos. For amplification, the BJT must be maintained in the active region by DC sources which keep the base emitter junction forward biased and the collector base junction reverse biased. The signals to be amplified are small changes around the DC bias point, which is known as the quiescent point or Q point. We solved the circuit approximately using superposition, breaking the signals into two components, large DC bias signals and small time-varying signals that oscillate about the DC signals. The IEEE notation for this has the total quantities denoted by lowercase letters with uppercase subscripts, the DC quantities by uppercase letters having uppercase subscripts, and the time representation of the small signals by lowercase letters having lowercase subscripts. Phasor quantities for the small signals use uppercase letters with lowercase subscripts. The second term of the Taylor series from calculus is used to approximate the small signals, creating small signal linear circuit models which are easy to analyze. Let's develop a small signal model for the BJT. First, we examine the base emitter characteristic. This is similar to the characteristic developed previously for a diode. The Q point is shown and can be calculated using a large signal approximation or, more accurately, with the Shockley equation, or can even be measured experimentally. We break V sub BE, that's the little v sub big BE, and the little I sub big B, into their DC and AC parts. Then we approximate them with the first two terms of the Taylor series, identifying the DC and AC components. Lastly, we let the small signal equations help us draw a small signal model of the BJT. Here before us we have the IV characteristic of the base emitter junction of the transistor. On the x-axis is little v sub big BE, or the total base emitter voltage. On the y-axis is little I sub big B, or the total base current. The equation, or what you would see on a curve tracer for this IV characteristic, is this curved black line. Let's remind ourselves a little bit about calculus. Remember, f at x could be written as f evaluated at x0 plus delta x, where x is x0 plus delta x. And that can be approximated by the first two terms of the Taylor series, f at x0 plus f prime evaluated at x0 times the little excursion delta x. Let's translate that into the terms for this IV characteristic. IB, the little I sub big B, is similar to f. Little v sub little be is similar to x. And so we have IB evaluated at big V sub big BE, which is like x0, plus little v sub little be, which is the delta x. And that can be rewritten using the first two terms of the Taylor series as approximately the total IB evaluated at big VBE, which is this black line right here, evaluated at this point right here, big VBE, and that gives us big I sub big B. So this green term right here is big I sub big B. Then we have plus f prime at x0, which in our case is the partial of IB with respect to VBE, or the slope right here at the Q point. Notice it's evaluated at Q down here, times the little delta x, which is little v sub little be. Now this derivative here is actually a constant, which you can see. You can evaluate it. It's just, you see it right here on the graph. And I'm just going to call that constant 1 over r pi because it has units of mhos or Siemens, which are the reciprocal of resistance. So I'm going to multiply that by VBE as it is up here. So in this case, you can say little I sub little b is equal to 1 over r pi, which is a number determined by the Q point and the Shockley diode equation, and multiplied by V sub BE, which is the little small signal excursion of the big V sub little v sub big BE. The little v sub BE axis is right here, and the little I sub little b axis is right there. Both quantities are 0 when you're at the Q point. Now, from this equation right here, you can see it's really the equation of a resistor here, having a value of r pi, with a current IB going in it, and a voltage VBE across it. Let's figure out how we can calculate r pi here. Notice that 1 over r pi is equal to this partial derivative here evaluated at the Q point. So here we have a little bit of calculus. 1 over r pi equals this partial derivative evaluated at the Q point. Putting a simpler approximation of the Shockley diode equation, where we ignored the -1 because this is a forward bias junction, in for little I sub big B, we can take the derivative here, and if we evaluate it at the Q point, where that's where little v sub big BE equals big V sub big BE, right here, we end up with this equation, Q over KT times this IS e to the Q big V sub big BE over KT. And this term in the braces, the IS and following here, is really just big I sub big B, as you can see right here. If you put in and evaluate on this black curve right here, you get big I sub big B. So let's just call it big I sub big B. And we can have big I sub big B divided by this quantity KT over Q. This quantity KT over Q has units of voltage, and we can call it a thing called the thermal voltage. And at room temperature, KT over Q is equal to approximately 26 millivolts. Let's look at the collector emitter circuit. It turns out this is much easier to deal with than the base emitter circuit because it's almost linear to begin with. IC, which is broken up into the DC and AC parts, is equal to beta IB, and then when you break IB into its DC and AC parts, you can see that little I sub little c is equal to beta times little I sub little b. And we just model that here with a dependent current source depending on the base current of beta sub IB going from the collector to emitter.